This example is demonstrating how we handle a network of bars acting as springs in conjunction with a beam or an element in the network that can have some rotation. So what we see here are two springs in parallel up at this top, and it's symmetrically balanced that this beam right here is rigid and there will not be any rotation that affects the system. There's another spring here that has same spring constant as what we have here. And then we have this longer bar on the right that has spring constant K2. And these two springs are connected with this rigid beam that we have here, given by ABC. And because of the way this problem is situated, and this force is a little bit off here, and that this can extend a different distance than this beam can in fact rotate. So we are going to go ahead and assume that this beam is rigid here, but we have rotation and the force is applied at the end of this bar down here, okay? And we're given a number of parameters, the lengths of A to B and B to C, and the force applied at the end. And what are we ultimately interested in? Having the displacement delta at the end, and it's going to be in units of microns. So if we go back to the video for the class, we can look at example 3.3, and essentially that's what we're being asked to solve in this problem. I've gone ahead and modified things just a little bit, but we're going to follow this example pretty closely. So we start off by drawing out a simplified network looking at the spring constants. And what is simplified, if you go back to example 3.2, you see how we're able to calculate this effective spring constant for the left side of the system. So for this branch right here, what you see, and that's this K1, K1, and this K1, you can find out that this is a 2/3 K1 effective spring constant. And it's not that hard to maybe do here. This is going to be 2K1 for the effective spring constant at this point, and then you have a 2K1 in series with a K1, and that will come out to be 2/3 K1. K2 is the right side, and then you see the ABC element right here, and we have our K3 acting in this bottom location. Now, we're going to do some equilibrium kind of like we would do with a truss, where we're going to look at what's happening on this beam and the forces that are involved at these three nodes, A, B, C. And yes, we're saying it's going to rotate, but it's not going to rotate that much. And so when we look at the equilibrium for the moments, we're going to assume it's flat, just to keep ourselves from having to do a little bit extra trigonometry. So here we draw out the three forces acting on the beam at A, B, and C, and then we can do force balance. So with the force balance, assuming that these forces are acting vertically, the rotation actually wouldn't be that big a deal. Because they'd still be acting vertically on a structure, and so this is the equation that we could write. The assumption about it being flat is more relevant to what happens when we start looking at the moments. And again, we're going to assume that there's very little rotation of this beam, and we're going to do the summation of the moments at this point A. And what are we going to have? We're going to have this F2 acting over this lever arm L AC, so that entire length. And we're going to have this F acting over this smaller lever arm AB. And so we can write out now a relationship for what we have between F2 and F. And since we've also done equilibrium up here for the forces, we can figure out what F1 should be as well. So we've got now expressions for the F1 and the F2, and they're in terms of the lengths of these parts of the beam. Let's go ahead and copy this information onto a new slide. like we see here. And we're going to now take a look at what is occurring with the rotation of this beam and how it's ultimately going to affect the displacement that we have at the end of the bar that has a spring coefficient of K3. So let's do a little bit of a review on similar triangles and how this angle of rotation could also be related with a trigonometric function of sine. Okay, so what are we talking about? We're saying, all right, let's just say we had a bar not dissimilar from what we have here, and we'll divide it into A, B, C, D nodes. And we'll say, you know, initially it was flat, but now it's been rotated here. And we have some delta A, delta B, and delta C, like you see here. And if we come up here, we can say, okay, there's some angle associated with this amount of rotation. And we're saying that this point D, it hasn't moved. We've just had rotation of these other locations. But there's obviously been displacement at A, B, and C. Well, we can also break the beam into different sections with lengths. For example, we have an LAC, okay? And this length, LAC, that was horizontal here, after rotation, it hasn't changed its length, but it has become what you might think of if we were to draw a triangle here, kind of part of this hypotenuse. Now, we're kind of making some assumptions because, like, if this were actually 100% pure rotation, right, this A point would actually move a little bit over to the right. But again, we're assuming small angles, so we can kind of say, okay, these things are not going to be changing. Like, this overall length is not going to be changing that much from this, assuming this is a small angle of rotation. Now, we can also look at some interesting attributes and think about, okay, so let's imagine there's a triangle that goes like this, all right, and so that has a length LAD for the hypotenuse, and we can say that this opposite side, which would be given by this delta A right here, okay, that could have some ratio that's going to be the same as the ratio of this length here, delta B, over this length now. So imagine there's a triangle like this, okay? Maybe I'll get a pen out just to make this a little more clear. Here we are. So we're talking about this triangle now, okay, like that. Okay, and so this length over here, this delta B, right, over this length LBD, all right, is going to have the same ratio as this length over there. Okay, so anyway, so that's what we're talking about. And similarly, we have a delta C is going to be have this delta C over LCD is going to have the same ratio as the aforementioned ratios. So that's one way to think of these displacements. Another way is to think of using a trig function. We can think of the sine of theta. All right, and what is that sine of theta? Well, that sine of theta is really exactly what we just wrote. It's going to be delta A over LAD. It's going to be delta B over LBD. It's going to be delta C over LCD. Okay, so we could also write that the sine, opposite over the hypotenuse, is given by these ratios that we have here. And the delta C over LCD, we can write out, you going back to this expression here, that delta or LCD is just this LAD minus LAC. Okay, so we've done a little bit of algebra and then maybe a little bit of review. Now we're going to look at our beam without this point D. All right, which, because there was no point D, all right, we're gonna say that we have ABC and it has some initial position as we've drawn here, which is of course here. And then if we say that the left side is going to lengthen, so the left side, so like this one section over here on the left, this one branch, if that has a larger displacement than the two branch, then we see that we'd have some type of rotation that looks like this. plus a displacement, because C is going to go down, right? In addition to B going down, in addition to A going down. And let's say that we have a delta 2 to describe this displacement of C and a delta 1 to describe this displacement A, right? And that that notation lines up with what we're saying here, that this is going to be the 1 branch and this is going to be the 2 branch. We can recall from our understanding of F equals K delta for a bar. So if we say this is an effective bar or an effective spring, like we have here, then we have the spring constant times the delta 1 equal to F1. For the right side, this branch 2, we can also say that F2 is equal to K2 times delta 2. And that's just using the spring constant that we have here, and the delta 2 and the force. And at this point, we can also think about the difference. Okay, so we draw this dashed line, we draw this theta here, and we can think of the difference between delta 1 and delta 2, which is going to give us this dashed line to this A. Okay, so at this point we can say, all right, we have a sine theta is going to be this delta 1 minus delta 2 over LAC. Right? And we can then also say that this delta 1, all right, can be remanipulated from this expression here, okay, to be 3/2 this. So we're just using what we solved for with equilibrium and this expression, and we can also do the same thing with delta 2. Okay, this came from equilibrium, and this comes from our relationship. Actually, these can be considered what are called constitutive relationships. It's kind of a fancy word to relate the forces in a system to the displacements in the system. And then we go ahead and we say, oh, well, I have a delta 1 and delta 2. I have this expression here for this sine theta. And I have now my expression here. So if I am interested in the displacement delta at the bottom of the system, I kind of want to know, well, what do I need to know? I need to know what's happening with B. Okay, how much has the B gone down? And that's going to be dependent on the rotation. So I kind of want to know what the rotation here as well. So that comes from this expression. And then we once again say, look, there's going to be a small amount of rotation. So we can use a small angle approximation for sine of theta. And that small angle approximation is going to mean that we can say that we're going to take out the sine and say that theta is approximately equal to this expression on the right. Okay, so now we've got, what do we know? We know these lengths, we know these spring constants, we know the force being applied at the bottom of the system. We know this length here as well, so we can figure out what theta is. And once we know theta, right, then we can get a better idea of what the delta is at the bottom. Okay, so let's recall. Now we just copy things over. And yes, this is a long and somewhat tedious problem, and it relies on our recollections in trigonometry and geometry, and our newfound appreciation for these relationships between force and displacement. So yes, we want to figure out what the total delta is. Still, how do we do that? Well, we can say that this bar goes down to delta 2. Okay, so remember C was up here, now it's moved down to here. And we've got our want to figure out what this delta B, or we might call it a delta 3, could be here. And so at least to describe kind of what's happening at B, right, we're going to have whatever displacement we had in C plus the displacement that we have at B, and then plus the additional displacement of what's happening through this bar the K with a spring constant K3. All right. So delta 3, going back to that use of either similar triangles or the trigonometric definition of the ratio of L3 to the hypotenuse, LBC, we have that delta 3 is equal to LBC sine theta. We're going to say that there's this additional, this deformation of K3, or the spring with coefficient of K3, and we'll call that delta 4. And then we're going to have our overall delta, which will be equal to, as we kind of hinted at, delta 2 plus delta 3 plus this delta 4. We can solve for delta 4 because we know what the force is, we know what K3 is. We can solve for delta 3 because now we know the angle of rotation and we know the length of LBC. All right, the angle of rotation comes from this expression. And so the result is that the delta at the end, all right, at the end is going to be equal to this quantity, where we've got our LBC sine theta right here. We've got our delta 4 right here. And we've got our expression for the delta 2 from, let's see, I guess it's from there, right here, going back to the previous slide, delta 2 right here, okay? So that is how we solve for the overall displacement in this system where we have rotation. And what are we going to do? We're going to plug in some values. We have a K1 equals 200 kilonewtons per millimeter, K2 is equal to 150 kilonewtons per millimeter, and K3 is equal to 100 kilonewtons per millimeter, and F is equal to the 1 kilonewton. Now, to make this problem a little bit simpler for the assignment, you can go ahead, I mean, you can implement all of this if you like in a calculator, that's fine. But I just want to point out that the script is actually available to do this for you if you want. You can go to the website, and we have this Colab available in a Google Drive, and you don't need to have really all these different libraries imported, but it's okay. We just really need NumPy, but because there are other examples, we can run them anyway. It's not going to take a significantly long time to do this. And then if you come down, okay, you see, all right, this looks similar, but this is example 3.2, so there was no rotation. And then this is example 3.3, okay, and there is rotation. So we have the 2/3 K1, right, calculated here, and this is just a screenshot from a slide. And the values that we're interested in using are already placed in this script for us. The calculations, the algebra, it's all done here. So if you just hit run, I guess the value is already there, and we can find out what the delta for this example is. So if you have different values and you want to just plug them in, you can do so. All right, thank you. That's kind of a long explanation for a somewhat complicated problem, and I hope you found it useful.